This video will serve as your introduction to solutions, okay, specifically focusing on differentiating between the different types of mixtures, one of which is a solution, and then also understanding the steps that we go through to make a solution, which are the steps having to do with dissolving. So first off, just some words to be familiar with. One of the complicated parts of this unit is the fact that we have solution, solvent, and solute, which are all S words. We have saturation, solubility. There's lots of S words in this unit, so make sure you keep them as straight as you can, as soon as you can. A solution is just a mixture of two or more substances. Each of those substances have their own names. Okay, we have a solvent and a solute always when we deal with a mixture. This is a physical change, right? Because when you make a mixture, you're not chemically changing either component, you're just physically combining the two different things. But one thing to be aware of right from the start is that not all mixtures are solutions. So it's important for you to understand what solutions are and what they aren't, so that when I say we're working with a solution, you better understand what things are categorized under that heading. So there are three actual different types of mixtures. Originally we talked about heterogeneous and homogeneous mixtures, which are really descriptors. Solution, colloid, and suspension are actually types of mixtures. The data on the screen kind of sums up the difference between the three. We'll be dealing with solutions. Okay, solutions are homogeneous mixtures. The solute particle, that particle size, the solute that dissolves is always really tiny. The composition of the stuff will be uniform. There'll be no particles settling out. Examples are like Kool-Aid, salt water, anything you can think of where you would tend to use the word dissolve. Another type of mixture is suspension, which is another one that you're fairly familiar with. They would be described as heterogeneous. They're heterogeneous because you have a very large particle being combined with another particle. If you mix them up, they can look pretty mixed, but given time, that particle solute is going to settle down to the bottom. They can be filtered, meaning they can be easily separated by physical means. Example would be like a mud puddle, sand and water, something where you can think of it being chunky, Italian dressing, right? Colloids then are a mixture that lies right in between a solution and a suspension. Okay. A colloid has a fairly large size particle being mixed into some background solvent. They don't settle though, even though they're bigger particles than the solution. They can't be filtered out. Okay. So in many ways they look just like a solution. They don't settle. They can't be filtered out. But in terms of are they homogeneous or heterogeneous, we call them borderline. And that's because usually you would think of a colloid as cloudy. The particle inside the mixture is so large that it actually inhibits your vision. Okay. Example would be like milk. Milk's essentially water with a very large protein mixed into it. That large protein is what you see in terms of the cloudy white nature. Now, one of the easiest ways to tell these three mixtures apart, the homogeneous solution and the heterogeneous suspension are usually easy to tell apart. But an easy test is something called the Tyndall Effect. And the Tyndall Effect is tested by shining a light ray through your mixture. And if the Tyndall Effect is seen, it's either a colloid or suspension. And if you don't see the Tyndall Effect, it's a solution. So in class, I'll actually show this to you. But here's an explanation of what the Tyndall Effect is. Okay, the Tyndall Effect is that when you shine a light ray through a mixture, the light ray scatters. What that means is the light ray bounces around between the particles in the mixture, and you can actually see the light ray traveling. It's like on those sunny days when the light's coming through your window and you can actually see the dust particles in the air. It's similar to that, what the Tyndall Effect is. The reason we see the Tyndall Effect in colloids and in suspensions but don't see them in solutions is about particle size. The fact that you have larger particles in the colloid and the suspension allows for the light to strike more particles and thus scatter, and you can see the ray travel. I will spend time in class specifically focused on this and demonstrating it to you so you can see it. But milk, Jello, which is really a colloid, things like that will exhibit the Tyndall effect. So again, a solution is a homogeneous mixture with really tiny particles. You can't filter it. It's totally mixed together. And I've already introduced these two terms also, solvent and solute. When we're dealing with a solution, your solvent is always your background dissolving thing. Water is what's known as a universal solvent, so most commonly you'll have water as your solvent. That's not always the case, but it's usually the case. One thing you can depend on as your solvent is the greater amount, though. Okay? The solvent will be a larger proportion of the total solution. If you look at the image on the right, those blue particles are the solvent molecules, which you have much more of than the golden particles. The golden particles are the solute, the things that get dissolved. They can be solids, liquids, or gases. You always have a less amount of them. Okay? And we'll have rules as this unit goes on in terms of why something could dissolve or how you know it will dissolve. But for now, you just have to be familiar with the terms solvent and solute. And if you mix a solvent and a solute together, that's how you get a solution. So do your best to learn those three terms early on because the math is hinging on you keeping them apart. So how do we dissolve something? This is something I've vaguely talked about other times, but we're going to make it very specific here. The process of dissolving is the process of dissolution or disassociation. And what happens is you have a charged particle placed into a charged environment. Okay? And basically you have an attraction between the ions in the solute and whatever the polar charge is on the solvent. Okay? The ions actually start to fall apart and become attracted to whatever your solvent is. So it's two steps, disassociation and hydration. Once you put the salt, for example, let's use sodium chloride, in water, the sodium chloride starts to be pulled apart by the water because the water is polar, and salt says, okay, I can get my charge balance from the water. Once those ions are separated, though, the water actually comes and totally surrounds the ions to kind of form a little cocoon of hydration to shield that charge. If you put a molecule in water, you're not going to have the molecule fall apart into ions because a molecule is not ionic. In terms of the molecules, what happens is you break your intermolecular force of attraction, and those intermolecular force of attractions are replaced by an attraction with the solvent. Okay, again, most likely water. So the big difference between ionic dissolving and molecular dissolving is for ionic dissolving, you actually fall apart into your ions. For molecular dissolving, you break intermolecular forces and you fall apart into your molecules, but you don't break bonds, right? You never break bonds just by dissolving. This is all a physical change. So if you have to have this charge attraction to make something dissolve, only polar and ionic substances can dissolve into each other. Okay, if you need the charge attraction to happen, then you need some kind of charge to exist. So you either have to have polar compounds or ionic compounds to have charge exist. Now, we already have some information about the ability to dissolve. We have our solubility table for ionic crystals, meaning not every ionic crystal dissolves, and I can spend more time talking about which ones do and why, but we can always check our chart to make sure that the ionic crystal we're working with will actually form a solution. Now, what's crazy is that all that information about charge causing dissolving to happen. We also know that non-polar things dissolve into each other. Well, that's weird. Now, really what's happening here is there's no charge force happening. Remember, for non-polar, we've just got our London dispersion forces, which are very weak intermolecular forces of attraction. So for most non-polar substances, it doesn't matter what is around it, it'll end up mixing. So you can mix oils pretty well with one another, and they will actually dissolve into one another, where if you mix oil with water, they won't dissolve, they won't form a solution. So that's all we're going to deal with for our introduction to solutions. In class tomorrow, I'll focus on demonstrating a lot of these concepts to you, and then we'll take it one step further. Go ahead and do the form and have a nice night.